In this module, we will consider motion in two dimensions. The language of how things move is known as kinematics, whether we are describing motion in 1, 2, 3, or even higher spatial dimensions. We need to understand the details of how we describe an object's location and motion through multiple spatial dimensions. Fortunately, by using vector notation, it suffices to consider motion in two spatial dimensions. The generalization to higher dimensions is direct. We will begin by considering motion in two dimensions. Let us first plot the path of a particle through space. The path is the coordinate position x of t, y sub t as a function of time. It is tempting to think of position as a vector, but it is really just a listing of coordinate values. The position vector is a special vector from the origin of coordinates to a given position. If we use Cartesian coordinates, then the position vector is easily determined. It is simply the vector given by using the coordinate positions as the components of the position vector. That is, we use the x position as the component multiplied by the I hat vector, and the y position as the component multiplying the j hat vector. Now, here's a warning. Don't try to do the same thing with the position given in terms of polar coordinates. You need to convert to Cartesian coordinates first. It takes a bit more care to correctly express the position vector in non-Cartesian coordinates. You first need to understand non-Cartesian unit vectors. Now, in our example, r0 is the position vector of the particle at t equals 0. r9 is a position vector of the particle at some later time, and each of the other vectors shows the same vector at an intermediate time. The displacement vector is the difference between two position vectors. In this case, delta r is r final minus r initial, and if we use the values of r final and r initial that are shown, we can just use the usual rules for addition of vectors using components to find the displacement vector. Let's move on and now consider velocity and speed. First, average velocity. If the average is taken over the interval delta t, which is t final minus t initial, and the displacement vector is given by the position vector at t final minus the position vector at t initial, then the average velocity is just this displacement vector divided by the time interval. If we assume that delta t is 2 seconds, then in our previous example, we can easily compute the average velocity. Average speed, well, it has a similar definition to what we had in one dimension. The only difference here is that in two dimensions, it can be a little bit more difficult to calculate the distance traveled, which is used in the numerator in the equation for the average speed. If we look at our example path, it will be rather difficult to calculate accurately the distance traveled between Ti and Tf. So let's consider a simpler example where we can do this more easily. In this case, our initial position points to the beginning of a semicircle and our final position the end of a semicircle. And because we have a semicircle here, half of a full circle, if we know that the radius of the circular path is 2 meters, then the circumference is 2 pi times the radius, and it's a semicircle, which is going to give us just 1/2 of that. So our distance traveled is going to be 2 pi meters, and we can use that to calculate our average speed. Now consider instantaneous velocity. This is given, or if we're given the position vector r as a function of time, the instantaneous velocity is simply given by the time derivative of this position vector. Now, the direction of the instantaneous velocity is tangent to the path of the object. Now, instantaneous speed is simply going to be the magnitude of the instantaneous velocity. And interestingly, the instantaneous speed is not related to the slope of the tangent line to the path. The rules we've just given for determining the magnitude and direction of the instantaneous velocity may seem to contradict some of the rules you learned for one-dimensional motion. In 1D, the speed was determined by the slope of the tangent line, but in 2D, the direction is determined by the tangent line and the slope has nothing to do with speed. The difference comes because we are looking at different kinds of plots. Let's look at this a little bit more carefully. Here, I'm showing you a three-dimensional plot where in addition to showing the path through the xy plane, I've also added an extra dimension showing the time. And now the path of the particle through space and time is shown by the thicker blue line that the yellow dot is following. Now, the tangent to the path in the xy plane gives the vector's direction. This is shown on the back plane of the plot. The slope of the path in the tx plane gives the x component of the velocity. This is shown on the bottom of the plot, and the path is shown by the red curve, the path in the tx plane. And finally, the slope of the path in the ty plane gives the y component of the velocity. The nice thing about using Cartesian coordinates and Cartesian components is that we can split the problem of the velocities into the x and the y components separately. We simply have to look at the slope in the tx plane to determine the x component of the velocity, and we look at the slope in the ty plane to look at the y component of the velocity. Now, let's consider acceleration. And first, average acceleration. If the average, again, is taken over the interval of the final time minus the initial time, and the change in the velocity vector is the velocity at the final time minus the velocity at the initial time, then we can calculate the average velocity very simply by just taking the ratio of the change in the velocity divided by the change in time. For instantaneous acceleration, given the position vector r as a function of t and the velocity vector v as a function of time, the instantaneous acceleration is given by the time derivative of the velocity vector, or the second time derivative of the position vector. Now, what is the direction of the acceleration? Is it tangent to the path? Well, possibly, but not necessarily. Is it perpendicular to the path? Again, possible, but not necessary. Is it perpendicular to the velocity? Possibly, but again, not necessarily. How about parallel to the velocity? Possible, but not necessary. How about tangent to the curve of the y velocity versus the x velocity? This is the answer. It's always going to be tangent to the curve of the y velocity versus the x velocity. This is analogous to the fact that the velocity is, the direction of the velocity vector is tangent to the curve of y position versus x position.